Okay, the last part of the structure and bonding chapter is going to be concerned with acid-base reactions. And I hope that for most of you, this is nothing more than a review. Okay, we have the Arrhenius definition, which just looks as an acid as a proton donor and a base as a proton acceptor. The equation that's important here is the dissociation of the acid. Okay, if we draw this equation, or if we extract a proper equilibrium constant from this reaction, this is the relationship that we're going to develop, and the value here is Ka. Okay, in organic chemistry, this is overwhelmingly the most important number, pKa. Okay, we're going to use this to express acid strength, and indirectly we're going to also use it to infer base strength. Okay, and pKa is just negative log the base 10 of the Ka value. Okay, so a strong acid, this reaction will go to the right, and if it goes to the right, that means that Ka is a large number, and pKa is thus going to be a small number since it's got a negative sign in front of it. In the Brønsted-Lowry definition, we're just going to add water to the equation, and we're going to look at the transfer of a proton at a carboxylic acid to water. Okay, and instead of having H+, we have H3O+. Okay, some other important relationships here. A strong base is a conjugate base of a weak acid or an acid that has a high pKa. A strong acid, it has a high pKa, and it's the conjugate acid of a weak base. And another important consideration is that acid-base reactions are going to proceed in the direction of neutralization to the weak acid-weak base pair. Okay, so let's look at a few representative pKa values for some of the organic compounds we're going to be talking about in this course and the course that comes after this course. Okay, so this is the functional group carboxylic acid. It's still a weak acid because its pKa is only 4.7, but it's among the strongest acids that we see in organic chemistry. So you probably occasionally you'll hear me and other organic chemists occasionally call a carboxylic acid a strong acid, even though technically it's a weak acid according to the Arrhenius definition. Okay, hydrogen cyanide, pK 9.1, and these are kind of going in order of higher pKa, from low pKa to high pKa. Ammonium chloride is 9.3. Phenol is very close to that at 10. Okay, in blue here, by the way, beneath each of these acids, we have the conjugate base. Okay, a thiol has a pK of about 11, water 16. This is a number that you have to memorize throughout all of the organic chemistry study, okay, that the water pKa is approximately 16. Okay, that's a value that needs to stick with you for a very long time. Okay, let's see here. That should not have a H. I don't know why that came through that way. Okay, an alcohol is about equal in pKa to water, and then an acetylene, if it has a hydrogen right on the triple bond like this one, it has a pK of about 26. We're going to deal with a lot of these compounds throughout this class and the next class. Okay, let's look at some trends for acidity and basicity. In the previous slide, you saw that the thiol had a pK of 11 and the corresponding alcohol has a pKa of 16. This is a general trend that we see in acids, that acid strength increases down a column of the periodic table of elements. Okay? Okay, and the reason for this has to do more with the stability of the conjugate base. Okay, so why is thiol more acidic than the corresponding oxygen compound? It has to do with the anion more than it does, or it has to do more with the conjugate base more than it does the acid. If we look at how this anion is distributed, okay, we have a negative charge distributed over a certain area, and here's a much smaller area here. So there's a greater concentration of excess negative charge in the oxygen species than in the sulfur species. Okay, and this accounts for why the sulfur compound is more acidic. It leads to a more stable anion after you remove the proton. Thus, the proton is easier to remove. Okay, if we look at the halogens, this is a trend that's important to remember, that HI is stronger than HBr, stronger than HCl, which is much stronger than HF. All of these in the Brønsted classification are strong acids, whereas HF is a weak acid. Okay, another important trend is that electron delocalization or resonance in the conjugate base will lead to an increase in acidity. Okay, here we see compare two compounds that have hydrogens on an oxygen. Acetic acid has a pK of a little less than 5. The pKa of ethanol is 16. Why is acetic acid so much more acidic than ethanol? It has to do with how the negative charge is distributed in the conjugate base. Here, if we look at the resonance hybrid, okay, so if you look, there are two individual resonance forms here, and what we see is that each oxygen only has to hold half of a negative. So we say that there's a delocalization of the negative charge. Okay? Whereas in this species here, there are no resonance structures, you're right. One oxygen holds all of the negative charge. Okay, and that's not quite as good a situation. Okay, so acetic acid is a more acidic compound because when you remove the proton, it leaves behind a much more stable anion. Okay, and that accounts for the higher acidity of acetic acid. Okay. Electronegative groups also have a profound effect on acidity. Okay, here's acetic acid here. If we replace one of the hydrogens with a chlorine, we see the acidity increases quite a lot, and the acidity increases even further if you replace all of them. Sorry, here I've left out a carbon. This is a very common mistake. Okay. All right. So the reason for this also has to do with the stability of the conjugate base. If you compare acetic acid with trichloroacetic acid, what you see here is that because of the individual dipoles of all the chlorines, there's an appreciable positive charge character at this carbon. Okay, so the fact that you have a partial positive next to a fully negative tends to stabilize the fully negative. Thus, it's easier to take this proton away. Okay, let's look at the last statement in that first part of this video, and that's that acid-base reactions are going to proceed in the direction of neutralization. Which direction does the following reaction proceed? Okay, think about this. If it's going to proceed in the direction of neutralization, that means that we're going to want to form the weak acid and the weak base pair. Okay, so if we look at the pKa values here, the pKa of water is 16, the pKa of acetylene is 26, therefore acetylene is the weak acid. Okay, because of the conjugate base relationship, or the fact that the weak base is derived from the strong acid and vice versa, we can say that hydroxide ion is going to be a weaker base than the acetylide anion shown here. Okay? Alright, so this reaction is going to proceed in the left direction. The acid-base reactions proceed in the direction of neutrality. Neutrality is toward the left in this case, toward the weak acid, weak base pair. And by the way, the weak acid and weak base are always on the same side of the equation. Never would you have a case where the strong base was paired with the weak acid. This is due to the relationship that we talked about earlier, that the weak base is the conjugate base of the strong acid. It can't be on the same side of the equation as the strong acid. Okay, this is something also that I want to stress in organic chemistry, and that's that sometimes we write compounds as anions and sometimes we include the counterion. The equation that you see here could have also been written this way, with sodium hydroxide instead of OH minus, okay? You should not let this confuse you, because this is an ionic bond, and thus this is two different ways of writing the same equation. If you look at the presentation throughout the book and through various other textbooks, you'll see the fact that sometimes the counterion is there, sometimes it's not. So you cannot let this be an issue that confuses you. Basically, what we'll see here is that our reactions are designed to produce organic molecules, and most of the time we're not going to end up with sodium in the final products. Okay, in this case we do, but we would do something with this structure right here. We wouldn't just leave it as that compound. Okay. Alright, so here's a problem. Pause it, do this problem, but armed only with the pKa data, answer the following questions concerning the reaction equation depicted below. Which direction does the reaction go? And which of the bases, or which of these four species is the stronger base? Okay, we kind of did that with in the previous slide, but let's go ahead and do that for this equation. Okay, We have a pK of 17 and a pK of 35. You may never have seen these, so you wouldn't know which was the stronger acid or stronger base, except for the fact that the pK value was given. Okay, so a higher pKa means the weaker acid. Okay, so we would see the weak acid would be on the right. Weak base would be the alkoxide. And the strong base and strong acid pair would be on the left. This reaction would go to the right because that is the direction of neutralization. That's where we are producing the weaker acid base pair, and that's closer to neutrality. Okay, here's another problem. Determine which of these compounds is the strongest acid. There are two trends operating here. Okay, again, pause it, do it before I start talking. Okay, the two trends. Acidity increases as you go down the periodic table, and acidity increases if you have electronegative atoms in the vicinity of the acidic proton. Okay, most of you probably never haven't memorized where selenium is in the periodic table. They're all in the same column of the periodic table. Okay, so we're comparing oxygen with sulfur with selenium. We should choose the selenium compounds as the stronger acids. Okay, and if we had to choose which of these is the strongest acid, we're going to choose this compound right here, because acid strength increases as you go down the periodic table, and electronegative atoms enhance the acidity. Okay, so this has the fluorines, and it has the hydrogen attached to the element farthest down in the periodic table. Okay, and the last topic I believe we're going to look at is Lewis acids and Lewis bases. Okay, so in the Lewis definition, an acid is an electron pair acceptor, or a nickname for that is an electrophile. Note that H plus is also a Lewis acid. The Lewis definition means that we can have things other than H plus serve as acids. And Lewis bases are electron pair donors. They're also known as nucleophiles. Okay, and the Lewis base, it's really not that different from the Brønsted base. Okay, so here we're going to react this molecule here known as an ether. This is a special compound. We'll just tetrahydrofuran, or THF. Is going to react with this compound, boron trifluoride. Okay, so we can see that the electron pair can actually react with the boron, which only has 6 electrons, and form this Lewis acid Lewis base adduct. Okay, all right, so this Lewis acid is reacting with the electron pair right here, and this is giving us the Lewis acid Lewis base adduct. So we see the BF3 accepts a lone pair, the tetrahydrofuran donates a lone pair. Okay, this forms an adduct. Lewis acid Lewis base reactions don't always form adducts, as we'll see in this case right here. Here, the lone pair reacts with carbon, but it displaces another atom, and this results in the bond of the nucleophile to the Lewis acid, or the electrophile. Okay, this reaction here is an example of something known as the SN2 reaction. which when it comes to like late October is where we'll be studying this reaction. Okay? Alright, so here's a problem for you. And again, try to pause it, try to answer it yourself before you listen to the answers. Designate each reactant as either a Lewis acid or a Lewis base. And note here that I didn't draw you the lone pairs. The reason being that would just make the problem too easy. Okay, you would see the lone pairs and say, oh, lone pairs, Lewis base. Okay, so we don't want it to be too easy. All right, so let's look at the answers here. All right, so in this case, sulfur is the Lewis base. It has two lone pairs. In this case, we're displacing the bromide. Okay, didn't want that. Okay, let's look at the next one. The next one may be confusing because the compound on the left we've referred to as a carboxylic acid. You've probably thought, okay, acid, it's got to be an acid. Well, look, the proton never left. The proton, the acidic proton's there, and it's right there still. Okay, so this is not donating a proton at all. Okay, so what's happening here is that we're actually using these lone pairs at oxygen here. They're reacting with tin tetrachloride to make a Lewis acid, Lewis base adduct. Okay. So here we see a unique occasion where the compound that has acid in its name is actually behaving as a base. Again, this is because the reaction is not occurring at the OH group. The reaction is occurring at the other oxygen. So this oxygen is donating its lone pair of electrons. Okay, so because of that, the Lewis base is the compound on the left. Okay, now let's look at this one. In this case, what we're seeing is the electrons in this double bond here are actually serving as the base for this reaction. Okay, and the bromine is acting as an electrophile. So the Lewis base is benzene. Let me draw this other hydrogen here too for emphasis. Okay, so we have these two hydrogens here. This is a reaction that's going to be important in chapter 12 of our textbook, and you'll see that. Many examples of reactions like that at that point. Okay, I believe this is where this chapter ends. Okay.